Perhaps I should resize this. So let's start with basic serial jobs. Partitions, yeah. When I showed earlier the animation of a cluster, it looked very homogeneous. You had 4 nodes of the same kind. De facto, modern clusters have multiple nodes with multiple kinds of nodes. So there might be nodes with less memory and nodes with more memories. There might be nodes with GPUs and without GPUs. There might be nodes with the latest generation of CPUs and nodes with the previous generation of CPUs, so on. Then typically certain kinds of CPUs are put into a partition. From the NAISS systems, perhaps partitions is most important on Dardel. And so here we have 6 different partitions. So there's the shared partitions. And it's a so-called SYN node, which is a kind of CPU node on Dardel, which has the least memory. And in this one, you can get part of a node. Dardel nodes are very, very wide. There are 128 cores to a Dardel node. And many applications cannot utilize that many cores in a sensible fashion. And if that concerns your applications, then you should be looking into running on the shared partition. The maximum job time here is up to 7 days. Then we have the main partition. Here you have 3 kinds of node, thin, large, and huge. Thin has a small amount of memory, large has medium, huge has more memory, and they are all exclusive, and you can run up to 24 hours. What does exclusive mean? We have written that down here. You get all the cores, all 128 cores for yourself. So don't use that for serial jobs or small parallel jobs, because for every hour you're paying 128 core hours out of your budget. And if you only, in particular, if you have a serial job, if you're only running 1 core, you don't make good use of your budget. Then there's the long, which is similar to the main, but it allows up to 7 days, but here we only have thin nodes. And then there's the memory job. There is the memory partition, which has large, huge, and giant. The nodes with large, huge, and giant memory. And again, that is inclusive. You get all the nodes to yourself, all this memory to yourself, and can run for up to 7 days. In these 3 partitions, main, large, and memory, you can ask for more than 1 node if you have an application which can reasonably use more than 256 cores, more than 128 cores of a single node. There are no partitions to tetralead. On Cosmos, there are partitions with respect to CPU and GPU nodes. And also there are different kinds of CPUs, which are in different partitions. And then on Kebnekaise, everything is in a single partition. So let's just look at an example. So what we are trying here is to run a simple Python script, which multiplies a matrix. How does that look? First, give a shebang. That's always a good thing to do because it enforces how the rest of the script is interpreted. You specify the job time as discussed before. It's a serial run. You just ask for 1 core. You can give your output, the output what the Python script writes to to the screen if you use it interactively. That ends up in this file processor. Process %j.out. Please remember the %j that gets replaced with the job number, which is unique, and that prevents jobs from overwriting each other's output. Then the errors, if your script throws errors, they get placed in this file. Here we have to select different names, error and out. If you want them in the same place, just write .out and then it goes here. Reminder on the cut $0, in particular if you're developing Slurm scripts and are not really so sure, that cuts the Slurm script into the output file here, such that it is documented what you specified here, in particular in case of problems. It will just show it is documented and you can see what you did wrong. Then we have to load the modules. Here, since this is a Python, we want to have a modern Python and we want to have access to NumPy, which on Tetralit is done with SciPy bundle. And then we can run like on a command prompt. Looking at Dardel, this is very much the same. This is a serial program. So here, very important, we ask for the shared partition such that we pay for only one core and not for all 128 cores when we are actually only using one. Over here we have scripts for Kebnekaise, Cosmos, and Pelle. And if that interests you, please look at that. I want to move on to OpenMP and shared memory. So this is actually quite interesting, and a lot of people should sort of pay attention to that. Shared memory programming, you have a single process which spawns threads. The threads get located on different cores, and then the workload gets divided, and the threads do that together. The aim is that you get a faster time to conclusion. All threads have access to all memory. There's essentially two ways of achieving that. One way is to take your code and put in directives or other constructs to spawn threads and to control threads. But the other one is also, I've written that here, using threaded libraries. Many libraries are programmed with threads, which includes many threaded BLAS libraries. And then if your program utilizes a threaded BLAS library, for instance, or threaded FFT library, or threaded whatever library, that as far as this is concerned, it counts as a shared memory program. And this includes, for instance, Python scripts using NumPy, if the NumPy builds on top of a threaded BLAS, which many of those do. So when executing shared memory application, unless there's a suitable default, one might need to ensure that only a single task is used, and this can be done by using the -n option of Slurm, for example, having a line sbatch -n1. Then we need resources to run our threads. I sort of outlined that. We are running multiple threads, and for that, we have to request cores, and that is best done with the -c option or -CPUs per task. These are two different names for exactly the same thing, so only use one. And so, for example, the following line sbatch -c8 request 8 logical cores. I will come back to what logical cores mean in a minute. On Tetralit, there is something in modern CPUs which is called hyperthreading, which means that two threads get put on a single physical core, and it takes a few instructions from the first thread, a few instructions from the other thread, and few instructions from the first thread, and so on. And depending on what these threads do, that might be faster or it might not. From many scientific codes, hyperthreading is not beneficial, and sometimes it's actually detrimental, but then there are also exceptions. Taking everything into account, on Zetralit, hyperthreading is not active, so running shared memory codes is quite easy. You just request -C8, for instance here, and you get 8 cores. You get 8 cores, and if you run that script, it will spawn 8 threads in all the threaded part. On the maximum you can specify here is limited by the hardware. On Zetralit, that is 32 cores. The rest here is very much the same. Then in here I have placed a few binding options. So when you set OMP proc bind to close, threads get bound as close to each other. That is typically beneficial if your application is bound by communication. For applications which are bound by memory bandwidth, spread binding might be advantageous. And on Tetralit, OMP binding using core binding, that all the threads get bound to a core, get allocated on a core, and are not allowed to move away from that core, is typically advantageous. And then you just give the name of your application. I mentioned NumPy beforehand. So in principle, this script here, you could use a Python script which uses NumPy. Then all the calls to NumPy will spawn 8 threads as given here. And it depends on whether this is faster or you're just or significantly faster or just burning allocations. Typically for a NumPy thing, I would expect 8 to be a bit high. 2 or 4 might be beneficial, and it depends what you're doing in NumPy. In particular, if you spend a lot of time in the matrix section, then you can get quite a nice speed up. If, however, you are just combining vectors, it might not be as beneficial. So if you run that, you have to experiment what is a good number for C. So for instance, if you start out at 8, take a second one, do a 4. Is 4 significantly slower, or is it or not? Then you get some idea is whether you should put 8 or 4. If 8 is substantially faster than 4, you might experiment with 16. If there's no benefit in going from 8 to 4, or whether actually going from 4 to 8 is detrimental, you might want to investigate with 2. Then also experimenting with spread and close is worthwhile. So now we get on Dardel. On Dardel, matters are a bit more involved. So the hyperthreading is active on Dardel. So if you want to run on Dardel, typically the shared memory partition, unless you can use all 128 cores, is beneficial. I explained that before. There's 128 physical cores to a Dardel node. And if you run in any other partition than the shared partition, you will be charged for 128 cores. If you have a program which only reasonably uses 4 cores, what I said beforehand on the serial programs applies here as well. It's very expensive to run on a main partition where you get charged for 128 cores and you only use 4 cores. Then the -C options of Dardel request logical cores. That is, if you ask for minus C of 8, you de facto get 4 cores, and the system attempts to run two threads on each core in an intermingled fashion. Whether this is beneficial or not is a matter of experimentation. Then it depends which compiler you are using. The Cray Clang compiler, which is the default, it's fully aware of the differences which behaves different. It is aware of that the system has hyperthreads on. So if we run this script here, as outlined here, where we bind two cores, then one thread gets placed on a physical core. So if we have asked for 8 logical cores, that is 4 physical cores, here our application will run with 4 threads, one on each physical core. Again, here we have 2 different binding policies. You can experiment whether this one or that one is better. On the other hand, if you want to experiment with hyperthreads, comment this line and uncomment that line. Then if you choose an OMP places of threads, then 8 threads will be utilized and 2 will be placed on each physical core. And then, yeah, it's a matter of experimentation. Try it this way, try it the other way. Running with OMP places equals threads, and what is faster wins. That is what you should use for your application. On the other hand, if you run this GCC 13.2, which is the most modern GCC on Dardel, then it reacts differently to the hyperthreading being active than the Cray compiler. Again, we ask here for 8 logical cores. This is very much the same. We can bind to cores. As far as that is concerned, cores and threads means very much the same. If you bind to cores, it will not restrict itself to only using 4 threads, once for each physical core. Remember, here with the 8, we have asked for 8 logical cores, 2 logical cores for each. 2 logical core for each physical core. So it will run still 2 on each. So if we want to disengage that, we essentially have to divide. We take the Slurm CPUs per task. This, if we put an 8 here, this becomes an 8. And we set OMP num threads, that is the number of threads, to 4. And then it will behave exactly as if we put the cores here. It runs 4 threads, 1 on each physical core. And if we have this line commented as shown here, then it will run 8 threads, 2 on each physical core. If you now tell me that's a bit involved, I can agree on that. So you might want to study that more closely, or if you struggle, give questions. Or where are we on time? Perhaps we can take a few questions. Any comments, any questions on this, on shared memory scripts?
So this option is not possible on PEL, or it's just not required?
Anyone knows, is PEL configured with hyperthreading?
Yes, it is, although you can reset that. But hyperthreading is on by default.
Okay. So you will not have a Cray compiler on Pelle. So most likely, if hyperthreading is on, it will behave a bit like that. So I would start with that thread and get experiment what you get. Does that make sense?
Yes, thank you.
Applications using MPI. MPI is a different scheme to parallelize application. It can be combined with the shared memory I have discussed above, but these scripts go a bit beyond the scope of this course. So if you have a pure MPI program, what you de facto do that is outlined here. So here we have 5 tasks. So we want to run on 5 cores, which may be on different nodes. That is in contrast to what we had beforehand. Beforehand, the threads always need to be on one physical node. On one node, you cannot run shared memory programming across nodes. It has to be on one node. So what we do with MPI, if we want to run on 5 cores, we run 5 copies of our program. And these exchange data. So what is drawn here, task 0 starts the whole thing. It might read an input file and distribute the data from the input file to all 5 programs. And then they keep running and exchange data as they go along. So here we have an example of, so these are Dardel examples, Dardel and Tetralead examples. The sample script assumes an MPI executable named integration 2D F90 in the submission script, and it takes input number as a command line argument. In these examples below, it is 10,000. So let's start with Tetralead, which is quite an easy architecture. So here everything is as before. You specify your account number, the time, and then the number of cores you want. On Tetralead, you can just specify I want to run on 16 cores. You get 16 cores on a single node, and then your program runs. Very important is here the last line. So here we have the name of the executable, and it is prefixed by something which is called the job launcher. On Tetralead, the job launcher MPP run is recommended. What is a job launcher? It's a program. It runs on the so-called head node or head core of your set, and it takes the executable as an argument, and then in this example here with 16, it makes 16 copies of the executable and starts one on each core. So so then that picture wouldn't look like that, but it would look that it starts with task 0 and continues to task number 15. And then these 16 copies run. If you have a look for Dardel, the first example here is asking for 2 full nodes with 128 tasks per node. So then this is a total of 256 cores located on 2 nodes. And so we have 2 full nodes all to ourselves. And then we can, since we have full nodes, we can run in the main partition. This is as before. We have our cut $0. We load the PDC module. And then here we use srun with an executable. Here the executable is named MPI hello. So srun here, that is the job launcher. It takes 256 copy of MPI hello. Half of them it runs on the first node and the other half on the second node. Oops, this went wrong. Then we have a second script, second example. Here we only need a partial node. So 16 cores, the program, it has, so for example, it might have been tested with this program that if you take 32 cores, it doesn't get significantly faster or it even gets slower. I have seen these things a lot of times. So 16 cores is determined that this is the best value for the program with the given input file. Then you can specify I want a single node, and on this node I want 16 tasks per node. On Dardel, 128 is the maximum number of tasks per node you can give because it is 128 cores. You have MPI process. You give your output and error file as before, and then srun with this thing. So here we have examples using a partial node and using two full nodes. If I want to run, let's say, on MPI on tetralead, I could specify minus capital N2 and minus tasks per node equals 32, then I would run 64. That would work as well. Okay, let's check. A few more comments. Oops. There was a typo, I just fixed that before. Asking for full nodes and possible tasks per node that should work on any cluster. Then depending on compiler and center, for the job launcher, you always need it, or you typically need a job launcher. srun or MPI run should be used in order to start your MPI job. On tetralead, it is MPP run. Normally, you need to load modules with MPI. On tetralead, it is built into MPP run. It typically figures automatically if you give an executable which MPI library was used. So it is not required on tetralead. Looking into the documentation, at some centers, core binding is recommended. If it, depending with MPI run, it is typically this type of a statement. With srun, it looks like that. And these days, it's typically 2-3%, which get faster by using core binding. I have in the past worked on machines where I could save 33% of the runtime by utilizing core binding. Okay. Any questions on these type of scripts? Serial jobs, shared memory jobs, or MPI jobs? Silence. Then I just stop sharing and give you over to Diana.
Yeah, thanks. So let's see, is this font big enough or should I increase it a bit?
It looks good for me.
Anyone else?
I would give it a tick up. Yeah, better.
Okay, I'm losing then the left menu, but that's okay. Okay then, so let's continue with some more examples. So in the last 45 minutes or so, I'll first go through some examples on memory-intensive jobs, IO-intensive jobs, some GPU examples, and then some job arrays, and then I'll give you some time to try some of these sample jobs on your own, including the ones that Joachim went through as well. Then we'll do a short wrap-up. But then memory-intensive jobs. So whenever you see an OOM, which means out of memory, be it in your Slurm output file or in the job. I mean, in the email that you get, if you have set that up for your job, that simply means that the memory that your application requires surpasses the one that was allocated for your job. And then what happens is that is going to crash, and then Slurm is going to kill that particular job. So then what to do when this actually occurs? So, well, simple answer is that, well, you simply need to allocate more memory to your processes, and there are different ways in which you can do that, and I'll give some examples. So you can either use nodes which have more memory per core, or you can use, well, the same nodes, but you simply have fewer tasks and you allocate more cores for each task. Or in some cases, for some applications, you can actually tweak the memory that the application is using. That is not possible in all applications. You do not need to know your application, but some do have that enabled, so it may be worth to check the documentation for your particular application. Okay, but simple fix, increasing the memory per task. So let's take, for example, an MPI application, and you've seen some examples from Joachim. So then, instead of just specifying, okay, how many MPI tasks my program should use, I also say that I want two CPUs allocated for each of these tasks. So then what this will mean in practice is that I will get double the memory, in this case, allocated to each task, than just having one CPU per task. Then, of course, I mean, you do need to make sure that, I mean, you allocate well, enough CPU cores in total for your application. How does a job script actually look in practice? So let's say that in this case, I want to run 8 MPI jobs, 8 MPI tasks, and then for each one of them, I want to have two cores dedicated. So then these are the options that I should include in my job script, and then I load, well, the module and the version of the module that I want, and I run my MPI application. So instead of simply allocating more cores per task, what you could do instead is to use this SBatch option mem per CPU and specify the memory that each of these CPUs need. So that is another alternative, and I will show you another one just in 10 seconds. So optionally, instead of using mem per CPU, you can use this option --mem and specify the value of the memory you want for the entire job. So not per CPU, but for the whole tasks whole number of tasks that this application is using. Now I'm going to give examples for that in particular. If you do want me to show it for other systems as well, then you should raise your hand. So because different applications have different memory requirements, instead of having a fixed number of a fixed memory associated with each node, it is fairly common that clusters have a hybrid architecture when it comes to the available resources. So on them, for example, the regular nodes have 256 gigabytes on each of these so-called twin nodes. But there are some further nodes in respect to the memory, ranging from half a terabyte up to 2 terabytes of RAM per node. And you can access these nodes on Dardel by specifying which partition you want to use, so be it main or memory, but you also should be adding this mem flag with the number for the memory that you actually need for your program, to ensure that out of these further nodes you get the one which is most suitable for your application. And these nodes are scarce in comparison to the regular fin nodes. So sometimes you may actually just want to increase the memory per task by increasing the number of CPUs per task, as I've shown you in the example higher up. So here again, check how many resources are available on the cluster at that point, and then choose the option that seems to give you resources the quickest. And all clusters are configured differently, and the hardware is different on different clusters, and this is typically well documented. But if you want to see on your own, from the command line, which are the features that different nodes have, then you can simply use this sinfo command with different options. So this will tell you, the available partitions and nodes and constraints that different nodes have. And also, this feature F, which is, let's see, it's not in this table, but some more information on different nodes. So as there was a question regarding hyperthreading at bed, I will just mention that you can read more in the documentation by following this link. Now, when it comes to IO-intensive jobs, so jobs that require a lot of reading and writing of files, this is something that is typically it's something we typically do not want. Sometimes we cannot help it because the application is just written that way, and we cannot change it. There are some solutions. Again, this depends a little bit on the cluster, and typically the solution is to use node local disks, and that is available to most clusters. Tetrally, Tele, I think at Kebnekaise as well, right, Brigitte? Now on
Yes.
yes, thank you. Now on Dardel, there are no local disks, but actually one can use this environment variable, NAISS TMP, or PDC TMP, which is going to point to the, so let me maybe show it instead. It's going to point to the Scratch directory. So CFC claiming Scratch, and then the first letter in your username, and then followed by your username. And then if you do have lots of IO jobs, then it may be worth to use this Scratch directory. Again, on that, this is not the node local disk, it's actually a RAM, which is going to be, if you use that, then it's going to make the total RAM available for the CPU compute lower. So it's a little bit of a trade-off. You need to actually test if that is helpful for your application or not. In general, if you do a lot of IO-intensive jobs, you should test at least once if it is beneficial to use these if it's beneficial to use the NAISS TMP or the TMP dir instead of using the project directory. Unfortunately, there is no one answer for all applications. Okay, but then if you do so if you do want to test if this directory is so the SNCTMP directory or the PDCTMP directory is beneficial, then you can just for example do a test where you copy the input data to this directory, then you run your simulation. What you do first, enter this directory, you run your simulation, and then you should not forget to actually copy your data back to your either the directory where from you submitted your job, or to copy it in another directory of your choice. I should mention that on Dardel, this Scratch directory is cleaned well, it's automatically cleaned, I think, after every 30 days. I'm not sure if they are taking other measures to clean it even more often if the need arises. Anyway, after your job is completed, or before your job is completed, you do need to ensure that you copy your data. For some applications, then it is actually possible to only save some temporary files to this Scratch directory. Again, I mean, this depends on the application. So, I mean, the input data can live in your submit directory, but the temporary files can live in this Scratch directory. Okay. Then I will move to job arrays. So some examples on when to use job arrays and how. So these are especially useful if you have many jobs, and I'm thinking of tens or hundreds or in some extremes, I mean thousands of jobs that are very similar and you want to submit at the same time. So initially, all the jobs which are submitted as job arrays have the same size in terms of the allocation, that resource allocation that they are receiving, the wall time limit, and all other SBatch parameters. Although I will mention already now that these can be tweaked after the job has been submitted or before it starts. So that is possible. And of course, I mean, the execution times will vary a little bit depending on the input data that each of these job arrays have assigned. And the way to indicate that, okay, I have job arrays, I want to submit the job arrays in a Slurm script is by using this array option, the array SBatch option. And there should be no space in here. And what is nice about job arrays is that, well, maybe your program is actually a serial one and you have problems making that parallelized using MPI or OpenMP. I mean, it's very easy to just take the same program with different inputs and incorporate that together with job arrays and run that as a more efficient way than just running serial jobs. So one note here on the maximum number of arrays that you can have per user at a time. This is very centered specific, as many other options with Slurm, but it's typically of the order of thousands of jobs. Okay, so I'm going to guide you through a very simple example on how this could be used. And in this case, it's like a very small Python script that simply prints a task number. You don't actually have to understand this. You can take your favorite code or rewrite this in your favorite using your favorite language. But So this just writes the task number. So the S-batch options are very similar to what you've seen before. I mean, we always have to specify an account that these jobs are billed to, a maximum wall time, and then resources in this case is just we are just asking for one core for each of these array jobs. And then the important parameter is this array S-batch option. And then we need to assign some values to this option. And in this example here, we are telling Slurm that, okay, it should submit in Slurm job that contains 10 arrays. Each of these 10 arrays having these resources that are specified in the job. So this accounting number, wall time, and in this particular case, one core. Although it can be more than one code, it can one core. It can be whatever you need. I mean, it can be 4 nodes each, for example. It really depends on your application and what is beneficial for it. But for the sake of the example, to make it simple, I mean, I said, okay, it's 10 arrays, each using one core. And then you need to load the modules that you need for this particular application, and then tell Slurm, okay, what are the tasks that each of these arrays should run. In this case, it's going to run this Python script, hello world array. Now, each of these different Python scripts are going to run this script for different arguments. The arguments in this case is the Slurm array task ID. And this is where arrays are very useful, because I mean, you don't want to run the same job 10 times. I mean, you actually want to run it with different arguments, with different 10 arguments, and then the argument can be Slurm array task ID, or you can have a different argument that is tied to this particular environment variable. So you can do further bash scripting and use other arguments for these different array jobs. Now, some comments on these arrays. So it does not have to start from 1. You can actually have, I think the default is 0, but I hope I'm not wrong. I mean, the default starts from 0, but you can specify any finite, integer number. And you can also have these indexes not being necessarily in step of 1, but it can use a different step. I mean, again, I mean, how useful is that? Depends, I mean, what you are actually using these Slurm task ID arguments for. You can also specify a list of numbers, and then this may be useful, especially as you are sharing your jobs with other people in the same project. You may want to limit how many jobs you're running at the same time. 4 is a fairly low number, but if you know that each of these job is using many resources, and then you want to be fair against your colleagues and make sure you are not eating up all the resources, then you may want to limit this. Again, I mean, it depends. If 4 again is a very low number, so you are free to not to use that at all, or have a much larger number. What is also useful is that you can specify a certain output for where each, an output for each of these job arrays. The important what are these? I'm not sure how I should call them, but so percentage J stands for the job ID, and then percentage A stands for the array corresponding to this job ID, and then specifying something except for the default, which is Slurm instead of process. Then you can redirect the output, either the standard output or the standard error, to other files, which are more suitable for your application. And then again, if you want to tweak further the arguments that your job array is, the argument that your application is using, then the environment variable to refer to is this Slurm array task ID. And this is also useful, I mean, if you want to, if you want to do some Slurm commands on top of these job arrays. Okay, now when it comes to GPU jobs, again, I mean, it is fairly non-uniform across the resources in Sweden. In the sense that that the way you are asking for a GPU, depending on the system you're at, is can be different. Some commands are the same, but some are different. One useful command again is the sinfo, followed by different ways of organizing the output. This is what it means. Interesting here is this option here for the output, which is G, which stands for the G resources, the GPU resources that cluster has defined, and then here is just grabbed over GPU, so that you only see the information which is relevant to the GPU nodes, but you can just use that without grabbing over the GPU. Now some a fairly small list on the GPU resources that are available on our supercomputers. Tetralist is a simple example in the sense that it only has NVIDIA T4s on each, on some of the nodes. For Dardel, the vast majority of GPU nodes are the AMD Instinct GPUs. And they are dual GPUs and 4 of them on each node. So this actually means that there are 8 GPUs on each Dardel node. And when you actually ask for GPU resources on Dardel, you are going to get the whole 8 GPUs for your job. So this is something you need to be aware of. You cannot share jobs on the Dardel GPU nodes with your other jobs or with other users. So this is the way Dardel is being set up. And for some, maybe some of you know that Dardel also has NVIDIA Grace Hoppers, although those are limited. It's a special partition, but Arrhenius will have plenty of Grace Hoppers. So that's the future for us. Now, when it comes to Alvis, it has many different NVIDIA nodes, the same as, NVIDIA GPUs, I want to say, the same as Kebnekaise. Cosmos has the A100 GPUs, and Pele has the L40 and the H100s. They are also NVIDIA GPUs. So, how can we actually allocate GPUs in our job scripts? So you recognize by now the options for the number of nodes and the number of CPUs per task. Now the new option here is GPUs per task. So in this case, I mean, we are asking that each MPI task is going to use, sorry, this is not nodes, I said it wrong, it's the number of tasks. It's capital N, which is number of nodes, my mistake. So in this case, we have one task, and then 32 CPU cores dedicated to that task, and one GPU dedicated to that MPI task. An example for Dardel. So in this case, we are asking for one full node. So minus n stands for number of nodes. One task per node. And then in the following is just specifying the partition. In this case, it's called GPU. Now, you've noticed that I have not actually specified any number of GPUs per node or number of GPUs in total. Again, on Dardel, when you are going to get all the GPUs which are on a particular node. If you are asking for one node, you're going to get 8 GPUs. If you're asking for 2 nodes, then you're going to get 16. Whether you use all of them or not, that is well, something you need to well, you simply need to ensure in your job script that you specify enough jobs to be run on these 8 GPUs. So for Alvis, you can specify how many GPUs you want for one node. You need to specify the type in the table before you, so that there are actually many different types for many different type of nodes. So the type that you will need to specify is either the V100s or the T4A100, and then the number of GPUs of that type in the following. Where was that? So here, sorry. So the number of GPUs of that type. And I'm going to skip these, as these are not nice resources, but you can read that there. Read more about them there. So how does the GPU, I mean the job script actually look in practice? Again, I'm going to show Dardel as an example. So similarly to what I had in the table before, so one node and one task per node, and specifying that, okay, I want to use the GPU partitions, and then I'm going to get allocated a node that has 8 AMD GPUs, so Instinct MI 200 or what it was. And then I can again redirect the output and error as I see fit. Then I do need to make sure that I load the correct modules that I need for this job. And then srun or whatever. I mean, srun my application. Sorry. If you do go into these exercises folder, then you can actually see different examples for Dardel and also for the other clusters. So there is a heap example, and then there is, I think it's a matrix multiplication or something like that. And then we also have a simple hello world example. So I can just open up the heap one. So there is there are 2 files here, the Python script and then the job script. So let's open the job script first. So what it does, it loads the needed ROCm module, and also, well, create Python. This is a Python script that is going to be run, and it's actually going to run this heap example py, which is just so what it does, it's let's see, sorry, so while I read this, it's not doing so much. It's not a a matrix multiplication. I think that we had it in a different example. Yeah, sorry for that. It's just doing a small test to see the GPUs. Then one thing to remember is that if you do use the GPU nodes on Dardel, then you need to use a heap code. I mean, a code written in heap. Otherwise, if your code is CUDA, then you need to use a different resource or use the Dardel gracehoppers, or well, the RNS gracehoppers, which are available. Okay, so some very small examples in the following. So you can also have, if you want, for example, to run many simple serial jobs at the same time. So you cannot, in some cases you simply have to use serial jobs because the application is not MPI parallelized or OpenMP parallelized. Then it is better that you gather, or well, in some cases, it's better that you run all your serial jobs into one job. This is an alternative, for example, to the job arrays that we have seen before. So what this simple example does is that it's so each of so the program is going to run on one core, and it's going to use a input, which is in this case is called data1. And then there will be another program which is going to use data2 as input, and so on. The important ingredients in this example is the use of exclusive, and what this means is that that this core that program is running on will only be used exclusively for this particular task. It's not going to be shared with program 2 and 3. So all of these will run, all these different programs will run on their own cores. Now, and then this means that this means that the application runs in the background. In this particular case, it means that this line will start running before a program actually finishes. So this ensures that all these different programs will be able to run simultaneously and exclusively on these different cores. You can have programs that run simultaneously, not necessarily using one core. You can specify more cores if there is a parallelism that is implemented in that particular program. Again, I mean, this may be beneficial if first of all, if these programs do have rather similar running times, because otherwise what will happen is if my MPI program only runs for 2 minutes and then all the others run for hours, that means that these 14 cores are going to be wasted while the other two programs are finished running. But if they have fairly similar running times, then it may be good to wrap them up into one job. Now, if you want, so again, I mean, this ensures that they are running simultaneously. If you want to ensure that they are running sequentially, meaning that the second step of the S-batch job will only start when the first one is completed, then you simply ignore the ampersand, and you just specify, okay, run my program data using 14 tasks with 2 cores for each task. So that will mean 28 cores in total. And only when this is finished, go to the second step and run, some follow-up program, my other program with some different input data and also different number of tasks and cores per task. Now, you do need to ensure that whatever number of tasks and cores you specify, and cores per task that you specify for these different steps of your job, that is equal or less to the number of cores you are actually specifying in your S-batch script. Otherwise, Slurm is going to complain, saying that, oh, yeah, trying to run something which I do not actually have resources for. Okay, so then this is more or less it when it comes